So we have talked about limits, and let's just recall the concepts regarding limits. So for example, we have this function here. We have y is equal to f of x. So if we want to figure out what's the behavior of the function, what's happening to f of x, as x approaches c, what's happening to this one here of the function, then that is looking at the limit of f of x as x approaches c. Again, we have different techniques to look into the limit of function. If the function is well behaved, then the limit of f of x as x approaches c would simply be f of c, if the function is well behaved. If not, then we would have to do certain techniques such as factoring, rationalization, or apply special triangle limits to check whether, or to determine rather, the limit of the function if at first direct substitution it's actually it's coming out as undefined. Then we also look into what happens if there are infinite limits with applications at vertical asymptotes and limits at infinity, which would be applied at horizontal asymptotes. Now, functions that are well behaved at the start, this is what we call them. We have well behaved functions. These functions are called to be continuous. As you can see here, if the function is continuous, there's literally no jump. Unlike this picture here, or unlike this graph here, wherein there is a jump from this part of the function to here. So this is not a continuous function. Continuity is important because it explores the behavior of the function at a certain number. So let's look at continuity. So a function is said to be continuous at c, at a number c, if the following conditions are met. F of c is defined, the limit of f of x as x approaches c is defined, and the limit of f of x as x approaches c is equal to f of c. If one of the conditions is not satisfied, then the function is said to be discontinuous at c. Let's check here. Let's check this one here at number 1. Not number 1. Let's apply instead of number 2. At number 2, we are asked to determine whether f of x, which is equal to 2x, for values of x in between 0 and 10, and 1.8x for values of x greater than 10, if this is continuous at 10. So the first thing to check is whether what's the value of f of 10, and it should exist. It should be not undefined. At this point, as we can see, f of 10, we follow the expression here above because it's less than or equal to. So we have 2 times 10, which is equal to 20. So we have this value. The next one to check is whether the limit of f of x as x approaches c, in this case 10, exists. For that to happen, the limit of f of x as x approaches 10 from the left should be equal from the limit of f of x as x approaches 10 from the right. Remember the existence of the limit theorem, that a limit exists if the left-hand limit would be equal to the right-hand limit. So, for our left-hand limit, the limit of f of x as x approaches 10 from the left, the expression that we use to the left of 10 is the one on top. So this would be the limit of 2x as x approaches 10 from the left, which will simply be 2 times 10. That would be 20. For our right-hand limit, we have the limit of f of x as x approaches 10 from the right. Values of at the right of 10, we use this expression, 1.8x. So we now find the limit of 1.8x as x approaches 10 from the right. This will be equal to 1.8 times 10, and that would be equal to 80. However, we can see here that 20 is not equal to 80. Hence, the limit of f of x as x approaches 10 from the left is not equal to the limit of f of x as x approaches 10 from the right. Therefore, the limit of f of x as x approaches 10 does not exist. And since the second rule is violated, the limit does not exist. Therefore, we say that f is discontinuous at c equals 10 or at x equals 10. It has to be that all three, f of c is defined, the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c should be equal to f of c for the function to be continuous. Unlike here where the limit does not exist, hence it is discontinuous at c equals 10. Now, if the limit of f of x as x approaches c does not exist just like this example here, then that kind of discontinuity is what we call an essential discontinuity. However, if the limit of f of x as x approaches c exists, it's just that it's not equal to f of c, then it's what we call a removable discontinuity. For example, let's look at number 1. We have f of x is equal to the absolute value of x plus 6 if x is not equal to 6, and 3 if x is equal to 6. Now, based on this function, it looks like there's something going on at 6. So let's take a look if it's continuous at 6. First, let's check what is f of 6. F of 6 based on the function is immediately equal to 3. So from there, let's now check if the limit of f of x as x approaches 6 exists. So we know that the limit of f of x as x approaches 6 from the left should be equal to the limit of f of x as x approaches 6 from the right. Both of these expressions will use the first expression, the absolute value of x plus 6, because it says as long as it's not equal, we simply use that expression. So we're going to have here the absolute value of 6 plus 6 equal to the absolute value of 6 plus 6, which is obviously the absolute value of 12 is equal to the absolute value of 12, which is equal to 12. Therefore, hence the limit of f of x as x approaches 6 from the left is equal to the limit of f of x as x approaches 6 from the right. Therefore, the limit of f of x, the limit of f of x as x approaches 6 exists, and that's equal to 12. However, as you can see here, f of 6 is equal to 3, but the limit of f of x as x approaches 6 is equal to 12. Since the limit of f of x as x approaches 6 is not equal to f of 6, the graph is discontinuous. Therefore, the graph for f of x, the graph of f is discontinuous at x equals 6. Now, if we are to redefine the function to make it continuous, we just have to make it equal, because this is a removable discontinuity. If here this is not this does not exist, then this is an essential. But here, since this is a removable discontinuity, we just need to redefine the function so that it will be the limit would be equal to f of c. So how do we redefine? Simply, since the limit of f of x approaches c equal 12, we just need to make f of 6 equal to 12. So instead of 3, we have to remove this and make it 12. Therefore, the redefined function of f of x would be equal to the absolute value of x plus 6 for x is not equal to 6, and then equal to 12 for x is equal to 6. This is how we redefine a function so that its removable discontinuity is, well, removed, and the function becomes continuous. So just some theorems on continuity. If the two functions are continuous already at C, then performing algebraic operations would be continuous also at C. Further, a polynomial function is continuous at every number. A rational function is continuous at every number in its domain. And for radical functions, if n is odd, n is continuous at every number. If n is even, f is continuous at every positive number. And that is continuity at a certain number C.